All right, everybody. So today I'm not here, obviously, but I thought that we could still do some notes anyway through kind of like a video thing. So please let me know what you think of this. If this is helpful, I might do this for more units and stuff like that. All right, so unit 4 is momentum and impulse. So first we're going to start with momentum. All right, so what is momentum? Well, momentum is basically just a measure of how hard it is to stop something. All right. So if we think about how hard it is to stop something, first we need to figure out how hard it is to change that object's motion, right? And this is what we call inertia, right? And then to stop something, you need to relate to how fast it's going. So velocity. And this would equal momentum. So it is the velocity scaled by the inertia. The inertia is the mass for linear. And the velocity obviously is v. And this would equal momentum, which is given the letter p. Yes, I know that p is for power and all that. This is a lowercase p, which is different from an uppercase p, which is different from a rho. I get it. The letters are annoying. I don't know why momentum is p. It just is p. That's just always how it is. So yeah, sorry about that one. Don't worry, we get into some more annoying letters later. All right, so we've got mass velocity. Mass times velocity gives us momentum. And keep in mind that velocity is a vector, mass is not. So when we multiply these two things together, we end up with a vector that is just the velocity scaled by the size of the mass of the object. Similar to F equal ma, right? So in fact, actually, Newton's third law, or second law, I've lied to you about. Whoops. Despite what you might think, it is not F equal ma. I know. It's actually kind of shocking because that thing is everywhere. F equals ma. It's not. It just isn't. It's F equals dp dt. But a lot of people don't know derivatives, and so saying F equal ma is a lot easier than saying F equal dp dt. And if we look at this, it's ddt of mv. So if m is constant, right, then F equals m dv dt, which is ma. So I sort of lied to you, but I sort of didn't lie to you. F equals ma is Newton's second law, but it's also, only if the mass is constant with respect to time, which like 99.9% of time in this, that will be true. So now when we're looking at this, right, if F equals dp dt, well, that means that F dt is equal to dp. And then by that, we get that integral F dt is equal to the change in p. And this is exactly what it is. This is called, though, impulse. So impulse, which we give the letter J. J is actually an interesting one for impulse. So a lot of people are like, oh, why is it J and not I? That's because I is used for current and a whole bunch of other things. But why J and not I? It's because in Latin, I and J are the same letter. Newton obviously was a Latin scholar, as pretty much everyone of his age was. And so it's kind of clever that impulse is J, because basically it is I, but in Latin, I and J are the same letter. So it's an interesting thing. You can talk to Dr. Dombrowski about that if you really want to. All right. So here, J, or the impulse, is equal to the change in momentum is equal to the integral of f, dt. There's no dot product because t isn't a vector. Now, this is very similar to work. Right? Where we get W is equal to delta K, or delta change in kinetic energy, is equal to integral of f dot dx. Right? So we use it exactly the same way. We use impulse exactly the same way. Really, what we talk about a lot with work is energy conservation. Right? So if there's no work done, then we have energy conservation, right? In this case, if f dt integral equals 0, then P is conserved. So if the integral of f dt is 0, then P is conserved. And what this means is f is 0 on our system. And this is just Newton's first law, right? This is Newton's first law. Which is basically that the velocity is constant if there's no force. Right? Because if there's no force, there's no acceleration. If there's no acceleration, then the velocity is constant. So that's Newton's first law. Right? Cool. Neat. We just proved Newton's first law using impulse. Great. But that's not really that useful to us. This is kind of an obvious statement, right? If there's no acceleration, there's no velocity. But this works for systems. Which is huge, right? Because what that means, if this works for systems, is that if all forces are internal, then momentum is conserved. So if all the forces are internal, momentum is conserved. That basically just says that if I don't have any outside net force, right, no outside net force, then I will have no impulse on my system, and therefore momentum in my system will be conserved, which means that the sum of all the momentum at the beginning will equal the sum of all the momentum at the end. And that allows us to solve some problems. Now, we have to talk about kind of a weird thing in this unit. That thing is called center of mass. Right, because something has to be moving at constant velocity, right? And because we have no outside force. So the center of mass of your system is what's moving at constant velocity. And this is the point at which outside forces act on an object or system. For linear, at least. For rotation, it's not totally true, but for rotation, it's not. So the center of mass is a weighted average of position by mass. What that means is we get that the sum of m sub I r sub I over I, so the mass at one specific location I times the location, or mass number I times the location of that mass for the same mass. So like object 1 at its position R1, and then we'd sum over all the total masses and all the total positions over the sum of all the masses. Right. So in this case, this would be the R for the COM for the center of mass. And then this is also a vector here. And so this would actually be equal to 1 over the total mass for a continuous object, integral of R dm. Right. And so that gets a little odd. It gets a little weird. But what we can see is that for most objects, so like, for example, if I have a sphere, right? Right. If I have a sphere and I want to divide by the total mass of the sphere, and then I'm going to integrate RdM. If this object has a uniform density, rho, let's say rho is equal to the total mass over the total volume, so 4/3 pi r cubed. And then that would give me that rho is also equal to dm over 4 pi r squared dr. Right? And so I can do this out and plug this all into this integral, and I can try to solve everything. But with my bounds, right, I'm going to sum over the total mass, so 0 to mt, right? But if I sum over the total mass, and I'm measuring my radius from the center of the circle, right, then I get that RCOM equals 0, because it's a symmetric integral, right? So uniform objects have a radius center mass at geometric center. And really, we're going to treat 99.9% of objects that way. Right? They don't normally make you integrate over the volume of an object when you haven't done volume integrals, because you theoretically have only taken AB calculus. Right? Volume integrals are a Calc 3 thing. So they aren't going to ask you to do that, although they sort of will later on, but we'll get to that when we get to that. At this point, we will not be doing volume integration. So really, we'll be sticking with the whole thing where RCOM is equal to 1 over the total mass times the sum of each mass for each object. This is what we're going to be sticking with. but I wanted to show you the integral nature just so for those of you in Calc 3, you could understand what we're doing, right, for continuous objects and why it's at the geometric center. But if you aren't in Calc 3 or if you don't know that kind of stuff, don't fret. That stuff won't be on tests or exams or whatever. Okay, so now we're going to do I would like to do a problem based on this, which I think is kind of a fun one. All right, so let's do, let's get more colors out here. I want it brown. How do you get up? Like an orangey brown. That's a good call. All right, orangey brown. So if I have like a boat dock. Right. I know it's not the best boat dock in the world. This isn't my Promethean board. This is my, this is my home computer tablet. So there we go. And I want to set up a boat. And we'll do this cool like Galaxy one for the water. Yeah, cool Galaxy stuff. And then I have a person on the end of the boat. Right. And this person wants to walk to the other side of the boat because they want to tie the boat off at the dock. Right? Seems perfectly and totally reasonable. They want to tie the boat off so that they can get off the boat and the boat won't move anywhere. Let's say the boat is 500 kigs and the person is 100 kigs. Right? And the boat is 6 meters long. Well, if the boat is 6 meters long, that means the person's going to walk 6 meters, theoretically, and get to the dock. So your answer might immediately be, oh, well, duh. Of course he can do that, right? But I want to find out how far the person is from the dock. After they walk across the boat. So in order to do this, I would find the center of mass of the boat because I know, all right, so let's actually back up for a moment. So I know that if the water is frictionless, so the water is frictionless, that's my first assumption. Water isn't actually frictionless, but in this case, we're going to treat it that way because we have to. So the water is frictionless. So what that means is that all forces are between the person and the boat. So if my system is the person in the boat, then all forces are internal. Right? And if all my forces are internal, then P is conserved. And that means that V final for the center mass equals V initial for the center mass, because the center of mass will move at a constant velocity. And if the boat is docked, it is stopped. So that means that the center of mass doesn't move. Right? So if I can figure out where the center of mass is, I can figure out that that center of mass needs to stay at the same location for the beginning and the end of the problem because momentum is conserved and the object isn't moving at the beginning. So I can find RCOM for the boat person system is equal to 1 over the mass of the person plus the mass of the boat times the sum of all the masses and their locations. So the person is at distance 6 meters, and the boat will have a center of mass at its geometric center, which is 3 meters away. Right? So then the mass of the person is 100. So RCOM equals 1 over 100 plus 500 times, MP is 100 times 6 plus 500 times 3. Right? So this will give me RCOM equals 1 over 600 times 600 plus 1500, which is equal to 3.5 meters. So the radius of the center of mass, so where the center of mass is 3 meters, 3.5 meters from the dock. Right? So I know that that has to stay exactly there, because as the person moves, the boat is also going to move. So now RCOM final, right, has to equal RCOM. But in this case, it's going to be still 1 over 600, because the person is going to not change mass and the boat will not change mass. But now let's look at a picture of what that looks like. So if I have my dock here, and I have my boat here, and I have my person here, right? This is my unknown distance, x. And then the center of mass of the boat will be at some y. Right? So now I can have 100 x plus 500 y. And now I have a problem. I know RCOM is 3.5. And I know that 1 over 600, I know that. I know 100. But I have x and y. And that's one equation with 2 unknowns. But looking at this drawing, I know that this is 3 meters. Right? Because the person is 3 meters away from the center of mass of the boat. Right? Because they walk to the other side of the boat. So now I know that y minus x is equal to 3. Because the boat is 6 meters long, its center of mass is at 3 meters, the person is on the other side of the boat, so they're 3 meters away from the center of mass of the boat. And now I can use this to solve this. So if I do y equals 3 plus x, I can plug that in. I'll get RCOM is 3.5. This equals 1 over 600 times 100x plus 500, 3 plus x, right? And so now I get 3.5 equals 1 over 600, 600 plus 1500, 600x rather. And so now I get 3.5 is equal to x plus 2.5. So x equals 1 meter. So that person's going to have a tough time tying their boat off unless their arms are extremely long. If your arms are really long, then maybe you got it. If not, you are going to have a rough time. So this is why if you're pulling up a canoe to a dock or something like that, you want to pull it up sideways, right? Or you want a person already at the front of the boat so that when you walk to the front of the boat, it doesn't change anything. Keep in mind that the heavier the boat, right? So the heavier this is, the less this distance becomes because the greater factor this 3 would have, right? So if your boat were instead 1,500 kilograms, then this distance would be significantly shorter. So this is why, like, for super big boats, it doesn't really matter. They won't matter at all. But for really tiny boats, like a canoe or something like that, this will matter quite a lot. So there we go. that's an example of a center of mass problem they might ask you to do, which is kind of a cool one. I like that problem a lot. All right. So now we're going to use conservation of momentum problems are often for collisions. And collisions are cool, except when they happen to you. Don't let them happen to you. Collisions are only cool in math and theory, right? So don't like go out and be like, oh, I crashed my car because my physics teacher told me to. No, I did. I told you that collisions are neat and interesting in a laboratory environment. Please do not go out in the world and cause mass chaos and collisions. All right, cool. Good talk. So for collisions, we have three main types. And one secret type. In full clickbaity fashion, we're going to save the secret type for the end. So there you go. So the three main types. The first one is elastic. So elastic is momentum is conserved. And kinetic energy is conserved. So think about this as like two bouncy balls running into each other. We're gonna go back to the cool like galaxy one. All right, so bouncy balls. Ooh. So like two bouncy balls collide into each other, right? So in this case, the kinetic energy is going to be conserved and the momentum is going to be conserved. So we actually get two equations, m1 v1 plus m2 v2. These would be initial equals m1 v1 final plus m2 v2 final. This is conservation of momentum. So this is conservation of momentum, right? And then we also get 1/2 m1 v1 initial squared. Oh, and keep in mind these are vectors, because that actually matters a lot for these. All right, m1 v1 naught squared plus 1/2 m1 2 v2 naught squared. Of course, kinetic energies was 1/2 mv naught. However, these are not vectors, because when we square them, we get rid of the directionality. And also, energy is a scalar anyway. So notice how this becomes rather interesting, because we have part of it being a vector and part of it not. So for part of it, the direction matters, and for part of it, it doesn't, which is kind of cool. Now you may be wondering how that works. The answer is, this part you can break up into x and y if they're in 2 dimensions. Oftentimes elastic problems are not in 2 dimensions, so you literally just have a positive and a negative sign. So this one might be positive, this one might be negative, and then, who knows what the ending will be. But basically we'll get 2 equations with 2 unknowns if we're given everything, all the information at the beginning, so the masses, the velocities at the beginning. The only unknowns we'll have will be v1 final and v2 final, as long as the masses aren't changing, which we assume they aren't, right? So m1 final and v2 or v1 final and v2 final are what we wouldn't get, and we'd have 2 equations with 2 unknowns, so we can solve that, which is pretty cool. So now 2 inelastic. Here we still have P is conserved. However, energy is lost. So not conserved. Right? So if energy is not conserved, then we can't use our trick that we had before. To use 2 equations with 2 unknowns. So we'll just have m1 v1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. And that's it. This is all we have. So in these problems, they have to give you extra info. That's because if they give us all this stuff at the beginning, we still can't solve this. Right? We only have one equation and two unknowns. So they might give us the final velocity of one of the objects at the end. They might give us an amount of energy loss so that we can actually use conservation of energy instead, but now we have to add in the extra loss term, right? Most of the time, they'll give you the information at the beginning and one of the pieces of information at the end. And then later on, let's say this is an FRQ, they might ask you for the energy loss, right? So then you would plug it into 1/2 mv squared plus 1/2 mv squared equals the final velocities and all that stuff at the end, plus some energy amount lost. So, and then you could subtract and find the energy loss. So there we go. So that's inelastic. Now the third type of collision is called perfectly inelastic. These are problems where objects stick together. So P is conserved. We have the max energy loss. So at the max energy loss, the objects stick together, meaning they don't bounce off of each other or anything like that. You can go through and prove that that's the maximum amount of energy loss for a system. It isn't fruitful, so we're not going to do that. I'm just going to tell you that it's the maximum energy loss. All right, so in this case, we have M1 V1 initial plus M2 V2 initial is equal to, well, if the objects stick together, then we end up with a sum of the objects mass, right, is our final object. And then that only has one velocity. So now again, if they give us all the information at the beginning, we can figure out all the information at the end because we have some V final, right? And it's not different, it's the same V final. In actuality, this is a function of two equations with two unknowns. I've just already plugged them in for you because basically in this case, we know that V1 final equals V2 final equals V final. Right, so this is the second equation that I would give, and then if I plug all that in and I do all this, I get the equation that I just showed you, the M1 V1 plus M2 V2 equals M1 plus M2 V final. All right, I have promised you a fourth secret type, and this one's definitely going to be your favorite, so stay tuned. Right, all right. This video is sponsored by WCPSS. Wake County Public Schools has been gracious enough to give your physics teacher a job. So, you know, there we go. Okay, enough ad baiting for explosions. Also called superelastic collisions. P is conserved. And energy is added. Oftentimes, the objects will start together. And split apart. Right, in true good explosion form. So for an explosion, we might get something like M1 plus M2 V initial is equal to M1 V1 final plus M2 V2 final. And yes, this is just a reverse. of number 3. So this is a reverse perfectly inelastic collision where they start together and they end apart. But you know what? It's so much cooler, right, to be an explosion. So energy can be added in a bunch of different ways. You guys are mostly used to incendiary explosions, which chemical energy is added, right? Because if I set a chemical on fire and then that creates a pressure differential, which then pushes the object apart, that's often how the energy is added, through chemical energy. But you can add energy through any other way. So yes, we are going to do a lab on this. And yes, we are going to use some kind of an explosion. It is not going to be the incendiary kind, because my sponsor, WCPSS, does not appreciate the incendiary type of explosion. So again, science is fun. Science is great. Let's keep the explosions theoretical. Thank you. All right, there we go. So those are the types of collisions. Now, other things. What if P isn't conserved? Bum, bum, bum. What happens if momentum isn't conserved? Well, then we have to use impulse. Right, so J is equal to the integral of f dt, which is the change in momentum. All right, so think about it this way. There is this thing that always goes around on the internet of like a 1969 Dodge Charger that is like, oh, my steel body Charger can beat the heck out of your Mercedes. Look at how stupid your Mercedes is because it crumples. Give me a good old-fashioned 1960s car any day, blah, 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 right? Because they were built to last. Yes, they were built to last. The major problem is that the way that momentum works, right, is that if I'm traveling MV at some speed and I'm going to stop, right, because I got into a car accident, right, I hit a tree, and I go from traveling at some velocity to no velocity, that is equal to the integral of f dt. Now, if f dt, if f is constant in time, that just gives me f times t. So if or we could look at it as average f. So looking at average force, right? That means that what I really want is an increased time of collision so that my force goes way down, right? So if I have an increased time of collision, I'm going some speed and I have some mass regardless, and I'm going to stop regardless. So this whole side is constant. Right? So if I have an increased time of collision, the overall force that affects me goes down. And that's good because your skull can only take so much force before your brains end up all over the beautiful dash of your 1969 Dodge Charger, right? So if your car doesn't crumple, then the time is much shorter for the collision. It will just stop. It has no give. It has no extended time of force application, and therefore it just stops. And if it does that, your force goes way up. Your head is going to slam into that beautiful, wooden steering wheel or whatever you did to restore your Charger, and it's going to crack open. So sure, your car will be around to give to your children, but you will not live to see your grandchildren. All right, that's a thing. This is also how airbags work. Or like stopping on any kind of squishy surface, right? The longer you make contact with that object, so like an airbag versus a steering wheel, right? The airbag has some give. meaning that you can push the airbag in some and it will apply that force over a longer period of time, meaning that the force that you experience goes way down, right? But if you don't have the airbag deploy, then when you hit that steering wheel, the steering wheel's not really going to go anywhere, right? It's going to stay where it is. And because it's attached to the car and it's built better than you are. So you might crack your skull open. You might break your vertebrae, right? Either way, you're in for a very bad world of hurt. So this is why airbags are really nice. And pretty much everything works this way, like brakes on your car. The reason that your brakes take time to stop your car is because they apply some frictional force to your wheels to stop them from moving. If they apply too much force, they set on fire, right? So they try to not set as much force up, and then therefore your car takes a little bit longer to stop. So that's a safety thing. Also, the longer the amount of time that you are slowing down, the lower the overall force on you, meaning that your airbags don't need to deploy because it's taking a very long time for you to lose your momentum, right? And therefore the impulse is applied over a very long time, and therefore you can slow to your velocity of 0 with a small amount of force that maybe just the friction on your seat is enough to stop your entire body, right? As long as the time is high enough. So this is how all of that stuff works, which is super cool and super useful, I think. All right. So now that's pretty much it. So that's all, folks. All right. So that's basically the entire momentum unit, momentum and impulse. That's all of it. We are going to do some problems. You guys are welcome to start working on the problems today. Please let me know what you think of the video. I really appreciate your feedback. If there's anything that I can do to try and make these better, or if you think they're a good plan to keep doing for different units and stuff like that, that would be, I can do that. So please let me know what you think. Don't forget to like, comment, subscribe, hit the bell so you get the notifications, click the things that make the dings, all that kind of stuff. All right, cool. If you run into any problems, send me an email. Bet. Have a good day.